We're going to do some more integration and continue our journey, and we're looking at instantaneous rate of change in an economics context. If we have the equation for the instantaneous rate of change of a quantity, and examples we've no doubt seen in the past might be to do with volume, might be the flow rate in a tank, alright, pipe coming in or out of a tank, area, displacement obviously with the motion stuff, and of course there's also cost. So we're going to look at that one in particular and some associated quantities as well. So if we have the equation for the instantaneous rate of change of a quantity, the amount by which the item has changed over a time period would be found by integration. We've seen that recently with to find the displacement or the change in position, we integrate velocity. Velocity is a rate of change. To look at how much the volume of a vessel's changed, we would integrate the flow rate, which would be integrating, if V is volume and T is time, integrating that quantity there. And that will give us the overall change in volume if we have limits of integration between A and B. Because it's to do with time, the duration would let us know what the terminals of or the limits of the integration are for the definite integral. In another one of my videos I talk about how things like revenue, what revenue is, and it might be given as a function R of X, where X is the number of units sold. So that's revenue. See my other video for that. Calculus in business or integration in business models. Cost also, which would be C of X, and profit, P of X. Sometimes instead of X it might be N units. Okay, you might get things like R of N. So see my other video there. And profit of course is revenue minus costs. Okay, see my other video in the same playlist for that. Focusing on revenue with the money coming in, we look at dr dt. If we're given that, the rate of change of the revenue in regards to time, the rate at which money varies according to time as a function of time, that has a special term. It's called the marginal revenue. Okay, so the marginal, it's known as the marginal revenue. Hence, this would be the marginal cost if we have dc dt. Sorry, dx, that is dr dx is the marginal revenue, how much revenue changes according to the number of items produced, and marginal cost is the change in cost per item reduced. So I was getting a bit mixed up with these two examples up here of velocity and flow rate. They're to do with time, of course. Marginal revenue and marginal cost and even marginal profit have to do with the number of units produced. So apologies for being inaccurate there for a moment. Now in terms of the marginal revenue, you can think of it as the extra bit of revenue or extra bit of money incoming that a company gets by selling one more item after a certain number of items have already been sold. It's that one more, what will the next one give us? Okay, so it's instantaneous. So that's one way of thinking about the marginal revenue. Okay, that extra unit, what would it provide? Okay, so there's that link to instantaneous rate of change you should be familiar with, because you've studied the derivative before. So now the rest of the video will focus on the use of integration to go from the marginal cost or the marginal revenue to the total cost of producing a certain number of items. Okay, So we have an example here, and we can see that on any day the cost per item for a machine producing X items is given by the equation dc dx equals 50 take 4e to the 0.02x, and we have restricted domain 0 to 200 items. Okay, of course we're talking dollars. In part A, we use the rate to calculate the marginal cost of producing the 100th item. So it's simply just an application of the given marginal cost function shown. Okay, so remember, marginal cost is a rate of change, and that's already been provided, so the first step should be quite easy. So when we're producing that 100th item, x equals 100, and the value of dc dx is simply a matter of substitution algebraically. So we have 50 minus 4e to the 0.02 times 100, and as an exact value we'll have 50 minus 4e to the 100, so that's squared, and as an exact value 20.4438. Okay, for the 100th item, so interpreting that means $20.44 for the 100th item. Okay, so for that 100th unit. Part B, what is the total cost? So total cost of producing the first 100 items. So that's the job of integration there. So we're going to go from the first item up to the 100th. Now because we start by producing 0 items, we need to put a 0 down here, and it's continuous. Even though they're discrete entities, we're integrating it as a continuous area. So we need to start the interval down as 0, and we do start with 0 items. Okay, before anything's produced there's 0, and then that goes up to 100. So even though both questions have involved 100, that is the 100th item there in part A, whereas this is all items from when we start at 0 through to 100. Okay, so hence the difference in the process. Okay, so we take our definite integral. So in regards to x, we'll have 50x for the antiderivative minus, now integrating e, so we have the reciprocal of 0.02, so 0.02 is a 50th, so the reciprocal will be 50. So we'll have 50 times 4, which is 200, e to the 0.02 x between 0 and 100. So I get, and I didn't show my working for that, that's in other videos, so this could be a question that needs to be done by hand, or it could be technology, it could be either way, but I get $3,722.19 for to produce the first 100 items. So for the production of first 100 items. Or units. So it is interesting that we can still model for discrete entities, okay, number of items, which is a discrete quantity, right? It's countable. We can still model it with basically what's equivalent to a continuous function, and thus, as you know, continuous functions are the work of can be made the work of integrals. So just because it's not a continuous quantity doesn't mean we can't use integration, so that's good to know. Lastly, we've got to calculate the average cost of production for the first 100 items. So the cost of production will vary because the cost of production is governed by a function. But we can find the average by simply looking at the total cost and divide by how many there are, and we've got 100 items and we've got the total cost from the previous part, which is $3,722.19, so we can write that in. So average production cost for first 100 items. Items. Okay. That means we're just finding, using the normal aggregate average formula, we have 372214 over 100, which rounded to the nearest cent is $37.22 per item on average. It's only an average. Okay, so remember, if you want an actual amount for a particular number of items, you need to do the instantaneous rate of change as we did in part A. But if you just want an idea and the average is suitable, you can do part C there.